Hello everybody. This is a video about rational functions, which is section 2.6, chapter 2.6. So we were just recently studying polynomial functions. So this relates because a rational function is just a ratio of two polynomials, right? So for instance, I'll just make one up. F of x equals x plus 1 over x squared minus 1. That's a rational function, all right, where you have polynomial here. And we're basically going to learn how to graph these. Mainly that's what this chapter is about, is understanding the graphs and the domains of rational functions. Now, as you know, when you have a fraction, you can't allow the bottom to be 0, right? So there are values here that are no-nos. In this case, 1 is not allowed because 1 squared minus 1 would give you 0. So I know x cannot be 1 in this function, which means it's not in the domain of the function. And the same with negative 1. X cannot be negative 1 either, because negative 1 squared is 1 and 1 minus 1 is 0. So there's two restrictions right there. And then we're going to learn how these restrictions affect the graphs. All right, so when we go to graph these functions, there's basically 4 major things we want to figure out. We want to figure out the zeros, which are the x-intercepts, right? There might be asymptotes. Now, asymptotes are basically like walls that the graph climbs up or skims across, so to speak, right? So imagine like a wall that a vine hits. What happens? The vine hits the wall and just climbs up the wall. So that's a okay analogy, I think. So we have zeros. There are such things as vertical asymptotes. There are horizontal asymptotes. And there are things called holes sometimes. Sometimes called points of discontinuity. And we've talked about the holes before, where whenever you have, I think we've looked at these functions briefly back in chapter 1, and you get your vertical asymptotes and your holes basically based on the denominator, right? So these relate to the denominator. Horizontal asymptotes, they involve like what happens when x gets very, very large, right? So for instance, if you look at, we're very, very small in a negative. So as x approaches positive infinity, what happens to the value of the fraction, right? So because the denominator is x is squared, and in the numerator x is not squared, that means as x gets large, the bottom of the fraction is going to grow at a much greater rate than the top, right? So you're going to end up with a small number over a very large number, which means it's going to go to 0. So by looking at this, just by looking at how the denominator is going to grow faster than the numerator, I know that as x approaches positive infinity, f of x is going to approach 0, right? Because when you have a very large number on the bottom of a fraction, you get a very, very, very small number. And the same is true, if we go negative. So as x approaches negative infinity, it's a little more confusing. negative. So as we go in the negative direction, well, negative squared is positive, right? So the bottom is going to remain positive even when x is negative. However, the top won't. The top will be negative. But the bottom is still going to grow faster. So you're going to end up with a small negative over a very big positive, which is basically still goes to 0. But it goes to 0 in a different way, and we'll talk about that when we actually graph this thing. All right, so let's take a look at the graph, and let's talk about what we get. So I've got x plus 1 over x squared minus 1. So f of x equals x plus 1 over x squared minus 1. All right, there it is. So let's see if what I said seems to be true here. So I said that, let me move this out of the way for a minute. I said that as x gets big, so here you see x is getting bigger, what's happening to the graph? It's approaching the x-axis, isn't it? And it's approaching 0 as a positive number, right? It's falling down onto the x-axis and skimming along above the x-axis in the positive region. Because, you know, when you're up here, when x is positive, you end up with a positive over a positive, which is still positive. But here, as x approaches negative infinity, you end up with a negative number, a small one, over a very large positive number. So you end up with a very small negative, because negative over positive is negative. So it still approaches 0, but from underneath. It goes up this way. Okay. So there's one asymptote. We have a horizontal asymptote right here at x equals 0. So I'm going to write x equals 0. In other words, the x-axis, that is the equation for the x-axis, is an asymptote. Because the graph approaches the x-axis, but never actually intersects the x-axis. All right, just to make the point more than obvious, I'll just put in some numbers. If I put in x of 1, I get undefined. So let's talk about that for a minute. Why, see if you can figure out, you can pause the video, why is f of 1 undefined? Did I already talk about that? I think I did. Oh yeah, I certainly did. It's just covered up right now. Why is f of 1 undefined? Well, it's because, as we said here, x can't be 1, because if you make x 1, it'll be 1 minus 1, which is 0 on the bottom. So we have undefined right there, x equals 1. So that's right, well, that's an asymptote, isn't it? I'll graph that for you so you can see it. Now, asymptotes are not part of the graph, but you can graph them usually with dashed lines to help you graph this on paper, right? So if I just graph x equal 1, there you can see that barrier, invisible barrier, that the graph seems to approach. Okay. So I put an f of 1 as a start to show you what happens when x gets large, right? So let's put in f of 10. Or let's put in 2. Let's put in 2 to start. So when f is 2, the value is 1. So when you go out here to 2, you're at 1. That's right there, right? Right there. Okay, and then if I put in 5, it shrinks to 0.25. If I put in 10, it shrinks again to like 1/9. If I put in 100, now you're down to 0.01. If I put in 1,000, smaller still. 10,000, smaller still. So as x is getting bigger, what's happening to the value of f of x? it is getting significantly smaller, right? Okay, now this is like so close to 0 you wouldn't even be able to tell the difference on a graph, but it's still not 0. So this graph approaches the x-axis as x gets large, but never touches it. All right, let's talk about that -1. What about -1? Well, -1, it's also undefined because, as we said earlier, if you make x -1 right here, you do get 0 on top. -1 plus 1 is 0. But you end up with 0 on the bottom as well, which is not allowed. So you get undefined. So you end up with 0 over 0, which is not a defined number. 0 divided by 0 is basically nonsense. So you end up with not an asymptote. If you notice at -1, there's not an asymptote, but there's a hole here, right? So if I put in, like, let's do f of c and add a slider. Okay, so here I'm going to just slide this, and we're getting close to, watch what happens above here as we get close to 0. All right, there's 0, and that's okay. 0 works. -0.3. What happens at -1? There it is. Did you see it? Undefined. Just wondering if we could actually see the point. That's not helping. Okay, so that's at -1 right here. We have a hole, not an asymptote. How do I know that? Well, the way you figure that out is you want to factor these before you look at them. It just makes them so much easier to read. All right, so I'm going to bring this down, and we're going to rewrite it as f of x equals x plus 1 over, if you remember, x squared minus 1 factors to x plus 1 x minus 1, right? And if you notice, you got x plus 1 in the numerator and x plus 1 in the denominator. It's okay to cancel those, and if I do cancel them, I end up with 1 over x minus 1. However, you have to remember that -1 is not in the domain of this, because -1 works here, right? If I put -1 right there, that's not a problem. -1 minus 1 is -2, and that it'll give you a number, right? But it'll give you a number that isn't, it actually doesn't exist on the graph, because originally there was an x plus 1 down there. So you would say where x is not equal to 1 or -1, right? So I can change f of x. I can simplify it as long as I stipulate that there's a restriction on that domain. Okay, so now if you get a term that cancels like that on top and bottom, that's a hole, right? So that's what creates a hole. This down here does not cancel, so this creates whatever causes this to be 0 is what creates that vertical asymptote. All right. So that's kind of an introduction. Let me write down everything I found. So there was a hole we found at x equal -1. There's a horizontal asymptote at x equals 0. There is a vertical asymptote we set at what, +1? Is that right? Yeah, x equals +1. And the zeros, well, there aren't any. I don't think. It doesn't look like you can make this value go to 0. The reason is when you try to make the top 0 by putting in -1, it makes the bottom -2. I'm sorry, it makes the bottom 0 as well, which is a no-no, right? So there are no zeros. So in this case, we just write that. And we could also find the y-intercept, which is 0, -1. You find the y-intercept by making x 0. So if you wanted to find that for the graph, you could certainly do that as well, which is useful. All right, let's take a look at the text here. So when you read through section 2.6, here you just describes to you what a rational function is. It's a ratio of two polynomials. The bottom can't be 0, of course. It states that. And here they're just showing you that as x gets very, very small, this particular function, in other words, as x is getting close to 0, f of x is getting close to -infinity, and so on. You can read that for yourself. We won't spend too much time on that. We'll just work problems for the most part. Here they're describing how to tell when you have vertical and horizontal asymptotes and what they are. Here's the definitions of those things. Here's basically a nice little layout of how rational asymptotes work in rational functions. So I'll let you read through that. If you have questions about that, let me know. And here they give you a couple of examples of that. And then here's some guidelines for analyzing the graph. So 1, find and plot the y-intercept by plugging 0 in, so that gives you a point on the graph. Find the zeros of the numerator, if any, by solving the equation. That just means set the top polynomial equal to 0 and solve it to get your x-intercepts. Remember, just like in this case, we see that -1 makes the top 0, but that did not result in a 0 of the graph. So it doesn't always give you a 0 of the graph, but most of the time it does. All right, then plot the corresponding x-intercepts. Find the zeros of the denominator, if any, by solving the equation the denominator of x equals 0. Then sketch the corresponding vertical asymptotes. Find and sketch the horizontal asymptote, if any, by using the rule for finding the horizontal asymptote of a rational function, which is back here, I guess, right? And then test for symmetry. That's something that you can, we learned about back in chapter 1, I believe, how to test for symmetry. Plot at least one point between and one point beyond each x-intercept and vertical asymptote, and use a smooth curve. They will always, just like polynomials, they are smooth curves, although they're not continuous like polynomials are, right? So in a polynomial, you could draw the whole thing without lifting your pencil. This thing, you can't. You can draw this part, but then you're going to have to lift your pencil up to draw this other purple part right here, right? So this is not a polynomial, but it is a ratio of two polynomials. Therefore, you do end up with curvy things just like you would with polynomial. All right, so let's look at some problems. Hold on, my computer's freezing up on me. Uh-oh. Weird. Okay, so I'm going to go down here to like problem 6. Let's look at this. It says in exercises 5 through 12, find the domain of the function and identify any horizontal and vertical asymptotes. So let's give this a try. Number 6. So we have f of x equals 4 over x minus 2 cubed. Okay. So we're looking for the domain. So it looks to me like any number is going to be okay except what? When it says find the domain, I see one number that's not going to work. It should be obvious to you. And it is 2, right? So the domain is, one way to write it is like this, all x's, such that x is not 2. And I don't see any other problems with this graph, so 2 is not allowed. Now, since 2 is not allowed and it's because it makes the bottom 0, then if I were to draw a graph, I know that over here at 2, I'm going to have an asymptote, a vertical asymptote, right? Because x can't be 2, but it can get infinitely close to 2. And as you get very, very close to 2, as you get really close to 2, this number is going to get very small. And when you divide a very small number and do a much larger number, in this case 4, you're going to get a very big number, right? So I know that as we get close to 2, this thing's going to shoot up like this. It's going to do something like this. Now at 1, I could probably figure this out. What's 1 minus 2? 1 minus 2 is negative 1, and negative 1 cubed is negative 1, and 4 over negative 1 is what? Negative 4. So at 1, I'm at negative 4. So at 1, I'm way down here. 1, 2, 3, 4, negative 4. So it really does something like, let's do something like this. Or maybe I'm not sure. Let me do a little more work. But I know I am down here at negative 4. Right? I'm down here at negative 4 when x is 1. And I know that I can't approach this. So what's going to happen here? As I get close, as I get close to 2 here, I'm still less than 2, aren't I? So that's a number smaller than 2 minus 2, which is a very small negative number cubed, which is negative, right? So it's going to do this. Yeah, I had that backwards. Now, on the other side, though, like if I'm over here and getting close to 2, let's say I'm at 3, what happens? Well, if I'm at 3, 3 minus 2 is 1, and 1 cubed is 1, and 4 over 1 is 4. So at 3, I'm up here at 1, 2, 3, 4. So I think it is going to do basically the opposite situation. It's going to do this. As it gets close to this asymptote, which is x equals 2, right? So that if I ask you for the equation of this asymptote, which remember is not technically part of the graph, it's imaginary, but we draw it on there to help us graph it. This is x equals 2. That's the equation for that line, that vertical line. Okay. Let's see. Now, what about horizontal asymptotes? So I've got a vertical asymptote. I'll just say VA for vertical asymptote, all right, is x equal 2. What about horizontal asymptotes, which I'll call HA? Well, that has to do with as x gets very large. And as you can see, as x gets really big, the bottom of this fraction is going to get really big. But the top's just going to stay 4. So you could be up at 1,000,000 on the bottom and the top's not going to change. So this is going to rapidly approach 0 as x gets big in a positive direction, past 2, I mean. So I'm pretty sure it's going to do something like this. like that. Now it's not going to ever touch 0, but it's going to get there pretty quickly. It's going to be close. And I think this is going to do the opposite. It's going to go up this way somehow, right? It's going to do this. Now let's think about why that is. If x gets very small in the negative direction, think of a very large negative number, then you're going to have a very large negative number, because when you take 2 away, you're still going to be negative. Big negative number minus 2, still negative. Cube it, it's even bigger negative over 4, right? So now you got 4 over this really big negative number. So it's going to get really close to 0, but it's going to be negative. So it's going to approach from the bottom. So your horizontal asymptote is y equals 0, which is your x-axis. Right? Y equals 0 is the equation for your x-axis. Ooh, and I need to correct myself up here, because I said x equals 0. That should be y equals 0. Horizontal asymptotes will always be y equal something, right? And vertical asymptotes will always be x equals something. Sorry for the mistake there. So, yeah, I'm glad I caught that. So y equals 0 is your horizontal asymptote. Now, I could also find this, even though I'm doing a lot more than the question asked, but I want to teach more than one thing at a time here. So, what about this point? What is that? Well, how do I find that? Well, I find that by making x 0, right? When x is 0, because x is 0 everywhere on the y-axis. So when I put 0 in here, 0 minus 2 is negative 2. Negative 2 cubed is negative 8. 4 over negative 8 is negative 1/2. So I know that number right there is at 0, negative 1/2. So that is your y-intercept. And I found that by simply replacing x with 0. All right. So I think I did everything that was asked of me. Find the domain, got it right here, and identify any horizontal and vertical asymptotes. I also did the graph. So let's see how I did compared to Desmos. So we'll go to Desmos and put this in. So we'll do f of x equals, that was what, 4 over x minus 2 cubed. Raised to the 3rd power. All right. So let's compare. Not too bad. It's much steeper than I made it, right? It should be like coming down at a much steeper angle right there. But you can see right here, there's that y-intercept that we found. You can see that it approaches the x-axis from underneath over here. It approaches the x-axis from above over here. There should be a vertical asymptote at x equals 2. I'll put that in there so you could see where it is. X equals 2 is right there. It's hard to see it approaching it, but if I zoom out, I think you'll see it a little bit better. Zoom out again. You can see the graph is getting closer and closer to it, but never touches it, right? All right, so we're all good. All right, I'm going to do one more, and then I'll end this video. So let's take a look at another rational function. So that was number 6. Let's look at number 12. F of x equals 3x squared plus x minus 5 over x squared plus 1. All right. Well, x squared plus 1, you can't factor that. X squared minus 1 you can factor, but not x squared plus 1. The zeros of this are, if you put x squared plus 1 equals 0, you get x squared equals negative 1, so x equals plus or minus I, right? Those are imaginary zeros. We don't need to worry about imaginary zeros. So as far as graphing this goes on the real number Cartesian coordinate system, which is what we're doing on Desmos, we're good. We don't need to worry about the denominator being 0. It will never be 0. Okay. What about the numerator? Can you make the numerator 0? So let's see. I've got 3x squared plus x minus 5. Can I factor this thing? If you can factor it, factor it. So 3x and x. Let's do a 5 and a 1 and see what happens. So that would be 3 and 5. I don't think so. If I switch the 3 and 5, that will just make it more extreme. So I don't think there are two numbers that multiply to 15 but add to 1, are there? The only other way I can think to find the zeros of this thing, if I wanted to find the zeros, is to use the quadratic formula. So I'm going to do that real fast. So there's your b is 1. So negative b plus or minus the square root. B squared is 1 minus 4 times a times c, which is negative 5, over 2 times a, which is what? 2 times 3, so 6. So that's negative 1 plus or minus the square root. That's 1, a double negative here, so that's 60, so 61 over 6. So it does have zeros, but they're not, very pretty zeros, but they do exist. So this does cross the x-axis. We can get an estimate for where that is. So if I do negative 1 plus the square root of 61 divided by 6, I get 1.135. And if I do the same thing again, but minus divided by 6, I get a negative 1.468. Okay, so those are my two zeros on the graph. So if I were to try to graph this thing, I know here's 1, here's 2, at about 1.1, so right about there we're going to cross the x-axis. Negative 1.4, so there's negative 1, there's negative 2, that's almost in the middle, it's going to cross the x-axis again right there. I know there are no vertical asymptotes because you can't make the bottom 0, right? You cannot make the denominator 0. So there's no vertical asymptotes. So no vertical asymptotes. Because this cannot be made 0. Horizontal asymptotes. What happens when x gets very, very large? Well, what happens when x gets large, you can just ignore everything except the lead coefficients, right? Those two. Because the rest of the stuff hardly matters at all. And I'm talking about, let's think of x being in the millions, right? Or billions even. These are going to stop mattering. They're going to be insignificant. And these will basically take over. So you can just look at those lead coefficients. Notice they're both x squared. So if there were x squared over x squared, they would basically grow at the same rate. So in that case, y equals 0 would be, y equal 1, because something divided by itself is 1. But this will always be multiplied by 3. So that means that the horizontal asymptote is going to be y equals 3 over 1, or just 3. So I know that on my graph, if I go up here to 1, 2, 3, there is a horizontal asymptote. Like that. So what happens here? Well, let's see. As x gets very large in the positive direction, right, it's just going to approach 3. So that means it's going to come over here. It's going to do, I'm assuming it's going to do something like this. Right, it's going to do something like this. And it's going to do the same thing here, because you do have some negatives, but it's still going to approach 3 from underneath in a positive way as you get big in a negative way, right? So as you go out here to negative infinity, you're going to have a negative number squared, which is positive, another negative number squared, which is positive. So you're going to get a positive over positive, but this one's 3 times bigger. So you're still going to approach that 3. And then it's going to do some stuff in here. Right? What's it going to do? I'm not sure. Can x equal 0 here? I believe it can, right? If x is 0, let's look at what is f of 0. So basically that would be 0. That would be 0. That would be negative 5. That would be 0. That would be 1. So you end up with negative 5 over 1, which is negative 5. So that means the y-intercept is negative 5. So it's going to go down to 1, 2, 3, 4, 5. It's going to do something like that. My best guess is it's going to do like some kind of well. I could be wrong. It's going to look like that. All right, let's see if I'm wrong. So we're going to go to Desmos and check this out. All right, so the function is 3x squared plus x minus 5 f of x equals 3x squared plus x minus 5 divided by x squared plus 1. And there she is. So looks good. Now, since you notice I wasn't sure, what I could have done is pick more numbers in here to get some more points, which would have made it obvious that that's what was going to happen. But that's it. So notice we don't have any holes in the graph because nothing makes the denominator 0, right? If nothing makes the denominator 0, you don't have any vertical asymptotes. If something does make the denominator 0, and that same number also makes the top 0, that's when you have a hole, right? Like when you cancel something out. And your horizontal asymptotes just have to do with what happens to the value of the function as x gets very, very large in a positive way and very, very large in a negative way. And as this one, as we discussed, goes to 3. Either way. All right, so that's enough for this lesson. I'll probably do about 2 more on this one. Might take a while. Thanks so much for watching, and God bless you. Have a great day.